So next up on stage is Mahsa Shoaran. Mahsa, in fact, got her PhD at EPFL in 2015, and then after some research experiences abroad, decided to return to EPFL as an assistant professor in neuroengineering at the campus Biotech in Geneva in 2020. Her research is right at the intersection of circuit design, machine learning, and neuroscience, and her mission is to develop novel devices, therapeutic and diagnostic devices to diagnose and treat neurological and neuropsychiatric diseases. Mahsa, the stage is yours.
Okay, thank you very much for the introduction. So I'm going to talk about neural interfaces, devices that can transform the way that we diagnose and treat brain disorders. So just as a brief intro, these are systems that record brain activity with various types of electrodes, as you can see here. And then at the core of this system is a neural microchip, a tiny silicon chip, which can process neural signals and then delivers electrical stimulation, targeted stimulation to specific electrodes in order to modulate the brain or suppress symptoms. So we call this a closed loop or a bidirectional interface. So this is the concept, and despite the great promise of this technology, unfortunately today we only have a handful of implantable devices for patients. Deep brain stimulation, or DBS for Parkinson, is a well-known example. And more recently, we see a trend toward building more advanced closed-loop systems, as well as brain-machine interfaces for restoring movement after stroke or paralysis. But current systems still have major limitations. They only have few channels for sensing and stimulation. They are very limited in terms of processing capabilities on the device, which limits their therapeutic potential. And current BMIs are still quite bulky, they are wired. In addition, we urgently need new devices for more common conditions, such as psychiatric disorders, Alzheimer's disease, and so on. So the challenge that we are trying to address in our Integrated Neurotechnologies lab is how to design more effective and efficient neural interfaces for a wide range of neurological disorders. Our approach to this is interdisciplinary. We combine integrated circuits with algorithms and AI and work in very close collaboration with physicians. In our lab, we believe that the next generation neural devices must be extremely low power and miniaturized, at the same time intelligent systems that are safe for chronic use. So to achieve that goal, we designed multiple generations of these circuits based on CMOS technology, aiming to improve the integration, energy efficiency, wireless operation, and also adding more processing power, more intelligence to these devices. So this interdisciplinary approach enables us to target many exciting applications, and I'm going to share 3 examples with you today. So the first one is a closed-loop system where we wanted to integrate neural biomarkers and machine learning algorithm directly on the brain implant in order to precisely predict symptoms and control stimulation. Our device here can record from a large number of channels and deliver responsive stimulation, and we verified this on brain recordings from patients with epilepsy and Parkinson's disease as a proof of concept, as well as in vivo in animal models of disease. And as you can see here on the top right, the device is extremely low power and small, meaning that we can even implant it with a minimally invasive surgery. So the second example is developing neuromodulation devices for psychiatric disorders, which, as opposed to Parkinson's, involve multiple distributed networks in the brain. So they are more complex to tackle. Our idea here is to design an implantable system which can measure and potentially correct disrupted communication between brain regions through targeted stimulation. We are specifically interested in measuring neuronal oscillations as well as connectivity in affected brain regions, and we have done extensive preclinical validation of our prototype devices And now we are pushing for clinical translation of our technology and planning first-in-human testing in patients with treatment-resistant depression. And finally, we are also very interested in pushing the limits for smart brain-machine interfaces. In a recent project in our lab, we developed a miniaturized BMI chip, as you can see here, which can decode the intended handwritten characters using brain recordings from a paralyzed patient. So for this, we developed a computationally efficient algorithm, which is inspired by the way that our brain selects visually salient objects in order to extract the informative neural signals and decode that with a very efficient hardware. So these are just some examples I showed you, but there are many other opportunities that we can explore using these intelligent miniaturized neural devices. So with that, I'd like to thank my team, and I'd be happy to chat more if you're interested. Thank you.